And there's a lot to this networking, but there's a lot of stuff we don't need to know to connect these computers together. So computers, when they first came out, they were standalone devices, you know. And of course, it didn't take long before they realized that instead of having one big computer, which they used to, we used to have mainframes and supercomputers. These were huge computers. When I first started here, we had an IBM 360, and it was a huge computer. And the terminals that we used had no real processing power at all. All they was is we call them dumb terminals. So all the processing power was in the mainframe. And then you had these terminals that you would use to send information to the mainframe, and then of course the mainframe would do all the processing. That was back in the days where we didn't have a lot of graphics. Everything was done in text. Text is neat because it takes so much little memory. I tell people why computers have to have all this memory now. It's primarily because of video. How much memory is required for the video. We display stuff in what we call pixels. Y'all have heard of pixels, right? Picture elements. So everything on the display, and I might go get my magnifying glass and let y'all look at the screen on this thing. Everything on this is done with little dots. On the LCD or the LED screens, they use little pipe things. And they only do four colors. They do, what's the colors that we can see? Red, green, and blue, and then shades of gray. That's all we can do. So we have rods and cones. I don't remember which one's which. One of them's for color, red, green, and blue, and the other one is for shades of gray. So at night, when you don't have any light, that's the primary thing you're picking up is nothing but the shades of gray. So with those techniques, we can basically do any color. So though we have what we call prime colors. Prime colors are what we make all other colors out of. But basically, there's some super prime colors, and they're red, green, blue, and then the last one is the absence of color, which is what? Black. So everything you see up on this projector up here, everything you see is done with those four colors: red, green, blue, and black. So primarily, we look on this, we'll see that we have three dots. They're red, green, and blue, and then it's on a black background. So if we turn them all off, then we see what? We see black. If we turn them on, then we see white, right? Understand? Well, not even white. If we turn them all on, and then we have all these little picture elements all beside them, but they're not picture, they're triads, and we turn them on a little different shades of those colors, right? Our eyes blend them together. So what we would do is eventually I realized that to increase power, it would be nice to share the processing speed between multiple computers. And so this is basically what happened with networking. So now we don't see many mainframes. We don't have a big mainframe here at the college. We have, because everything is what? Is shared. Now we do have computers that serve one function in life. We call them file servers. So what's a server, by the way? So on a network, what's a server? What would y'all think?
Like the cloud?
Well, the cloud is going to be hosted by a server. A cloud is nothing but a file server. So we got our own cloud here, but it's not over the internet. It's right over here, and we have a 6 terabyte file server over there. And all a file server does is it's where you store data at. You can restore and retrieve data. So a server on a network is a specialized computer that is set to share its resources. That's all it does in life. It shares its resources. So we have print servers. What does a print server do? Shares printers, right? You understand. So So if I share my printer, and it's built, a lot of it's built into the operating system now. So I've got a printer over there, it's hooked up to the network. Inside that printer is a file server. So what I can do is I can use that printer and everybody over. So Allison doesn't have a printer because she uses mine. I can be over on A building and I can print stuff over here. I do it accidentally a lot. So it's a computer that shares its resources. We have file servers, we have domain servers that basically allows us to not only let me look at my power server. So what we do with networks, it allows us to share resources. And of course, originally we didn't have the internet. We had just local area networks or just local networks. Then we have what we call clients. So clients are computers that use the resources of a server. Okay. And of course now a lot of your computers have the ability to serve both those, a lot of your operating systems. What's an operating system? So what you got to do is you got to understand a computer does one thing in life. A computer runs programs. That's all it does. So every time you turn a computer on, it automatically goes to a certain section in the memory of the computer. It's in what we call read-only memory or non-volatile memory. And it looks for a program. Call it the boot routine. So the process of a computer loading its operating system is called booting the computer. So every once in a while, they was talking about a guy on one of the shows I was watching, 2020, I think. And was talking about he actually did a full factory reset on his phone, so they couldn't see his text messages and everything. So right now, when I turn this computer off, and then I turn it back on, we call that booting the computer. And then what that does, and it got the technique because that's basically what it used to be. It used to be so dang hard to start a computer up. They said it's like kicking it, right? You understand? Booting machines usually take a pretty good while. They got a lot better over that. So what we have to do is we have to have a section of program. So inside a computer we have a central processing unit. What does a central processing unit do? It actually does what? Runs programs. That's all it does. Now, of course, most of your computers have more than one processor. Now we call them cores. And then inside the computer, we have memory. So the computer runs programs that are in the memory of the computer. We have two categories of memory. We have ROM, and then we have RAM. And ROM stands for read-only memory. And this is a lot different than when I first got into it. Now, originally on the ROMs, the only way you could change the programs that were in the ROMs is you had to literally change the integrated circuit. But memory has evolved quite a bit, and we can actually, we call it flashing. We can actually flash the ROMs in the computer now. You don't do that very often because if you lose this, so an operating systems are the programs that make the computer operate. So every computer has an operating system. So these are the computers that these are the programs that make the computer operate. So everything this computer does is controlled by a program. Everything. me up here typing on this keyboard. This computer has no idea what a J is. All it is just an input. When I press a button, it's an input. But it knows where that input is coming from. It's like a PLC. So a PLC, we say, okay, this stop button is hooked to this port. And then after that, we can use that. Well, that's what it is. This G input is hooked up to a port. So what we put in the ROM, so now the ROM, they use a technique called double EEPROMs, which are electrically erasable programmable read-only memories, which means on most of your computers now, you can actually flash this ROM. You can actually upgrade the ROMs. We can even do that on the PLCs now. So one of the first things they tell you to do when you get most new PLCs is to, once you load in your application, like RS Logic 5000, one of the first things they want you to do is check to see if there's a ROM update for your PLC to make it more compatible with the version of the RS Logics that you're running. But in the ROM, we have something we call a basic input-output system. It's in the ROM. Because all it is just enough to get the thing started. Okay. Now this is this computer right here. These guys right here, everything is there. So everything's in there. So it doesn't have a split. What they decided to do on some computers, instead of trying to put the whole operating system in ROM, they decided to put a basic operating system in the ROM and then load the main operating system off a mass storage device like a hard drive. Now what's nice about that, it gives you the ability to change your operating system. So all the BIOS does is just hold the programs that tells it to go out and do what? Well, it gets the computer operating. It goes out there and initializes all the programmable integrated circuits that's out there inside the computer, initializes those to make sure the ports and everything are working. On these computers, it runs what we call a power on self-test. And PLCs do that. So anytime you plug in a PLC, you'll see lights start blinking. Well, what it's doing, it's running its power on self-test. It's running this little self-test to see if it's operational enough so you can do what? So you can put programs in there, right? You understand that? And of course, most people refer to this as the BIOS. We use a lot of acronyms in computers, a lot. And some of them are not technically acronyms. So what is an acronym? Anybody know what an acronym is? It's when you take a phrase, well, it's not an abbreviation, it's when you take a phrase and you take the first letter off each pertinent word. Sometimes we use ands and words that we consider to be not pertinent, and because it makes a word, and you use that to form another word. So BIOS is a true acronym. It stands for a phrase, which stands for what? Basic Input Output System. So that's the definition of an acronym. Over time, we've let that slip. Now they'll take the first letter off a phrase, and we just repeat the letters, like SEC, or something like that. But they still call those acronyms. It's not really a true abbreviation because you're only using what? You're only using the first letter. So the BIOS would be in the ROM. It's definitely in the ROM. These PLCs, normally the whole operating system is in the ROM. And so what you do on those, it's still got the sequence that goes out and runs a self-test, right? You understand? And then initializes this when you first turn it on, or when you do a reset. Used to on our computers, we had a reset button. And what you did when you hit that reset button is you forced it back to run the boot sequence. It would actually go back in the ROM, and it would actually run everything. What they've added, we call it restart now. So now when you can restart your operating, we call that a soft boot. Which means it don't do all the stuff. It don't run all the power on self-test. It just goes back and reloads your operating system. It don't do all the stuff that's in the BIOS because the computer's already wired. configured. Warm start, so we called it a hard boot. A hard boot would be when you actually plug the computer on. So that would be like on your cell phone, you pop the battery out of it, if you could, and you put the battery back in. That would be what we call a hard boot or a cold boot. That basically reinitializes everything. If you just do a restart, go ahead. With a what? Well, it all depends. My wife does it every once. She's got hers on hers now. She's got I can't remember what she's got, but it's an Android operating system, and it won't charge unless she does a restart. And then if she restarts it, it charges. They just started that lately, so I don't know. So the ROM in the computer will hold, for most PLCs, the ROM holds the operating system. On these computers, the ROM holds a BIOS, which is a basic operating system, which is what your cell phone does. Because what do you do on your cell phone all the time? You upgrade your operating system all the time, right? So the operating system is so if you pop the battery out of the thing and stuck it back in there, odds are you'd lose your operating system. You probably have to redo that. Are we okay? Most of your phones now don't let you do that, which is a shame because you used to keep extra batteries charged up, right? So then we got RAM. RAM stands for Random Access Memory. We actually add some, we call it Random Access Read-Write Memory. I like to call it that, even though it don't fall into it.
Because the RAM can read and write
the ROM, we technically from our end, we can't change the contents of ROM unless we run a special application. So I could not go into this computer and reflash that ROM. I can't do it. But I could do it if I ran RS Logic 5000 and it says, okay, there's a new version for your flash it. Don't turn your computer off, because then you've screwed the little basic element. So there's still some ROM in there that you cannot change that allows you to flash the rest of the ROM. So this is where our application. So every time I download an application into this PLC, it is going in RAM. So this operating system on this computer runs out of RAM. And that's why we have to have so much RAM on these machines, because the main operating system is in RAM. So the operating system I'm using on this computer is called Windows 7. My computer over next door was originally running Windows 7, but it crashed, and what did I install on it? 10. How could I do that? Because it's a disk-based operating system. It's not in the ROM, it's loaded off a disk into the RAM. The BIOS tells it to load the operating system off the disk drive, which makes it really neat. So what's nice about information that's loaded off disk and put in RAMs, we can change it, right? You understand that? Which is pretty neat. Now these things communicate with over buses. Buses are basically just a group of conductors that carry like information. So we have a unidirectional bus that we call the address bus. By the way, the CPU only, so a language, we speak languages. We speak English. Anybody know any other languages besides English? So, I don't. Well, I knew a little Japanese. I knew how to cuss in Japanese. I was in the Navy. I don't do that anymore, guys. So we got over. Yeah, I open. Yeah, there you go. Yeah, I know. That is a loud compressor. We talked about what we do. So we were over in while the Shah was still in power, when I was in the Navy, we went into Iran. And we had a bus driver that would drive us around to show us things, and he couldn't speak any English at all. When we got there, so we had a translator. We had to carry a translator all the way. And we taught him how to cuss. So it was so funny. It was funny then. It wouldn't be funny to me now. I wonder what happened to those guys. So the only language the CPU speaks is a binary language. And it's technically referred to as, I need to erase some of this. Are we okay? Yes, no? So it's a binary language. By the way, there's on our website, there is a glossary of terms. So all this would be in the section called computers. So the language these guys speak is a language that we refer to as machine language. Some people call it object code. And this is a binary language. So what we have is we have all these binary combinations that we refer to as operational codes. Most people call these opcodes for short. So these are binaries. These are binaries. And what the processor does is when you originally reset it or originally start it, it goes into a phase called the fetch phase. It outputs an address on the address bus. It sends it into the ROM memory, and what comes out of that is an opcode. So the first instruction this thing actually executes as an operational code. And then once it pulls in the opcode, it translates that and says, okay, this is what you want me to do. I want you to add two numbers together. Then what it does, it switches into what we call the execute phase. And it's kind of blurred on today's computers. In the execute phase, it does what the opcode told it to do. And then once it gets through with the execute phase, what does it switch back again to again? It goes back into the fetch phase and it looks for another opcode. Then it switches to the execute phase and does what that opcode told it to do. And it's just constantly back and forth, back and forth, back and forth, back and forth, back and forth. Now it's kind of blurred now because we have programs that are multi-threaded, which means they have modules that can run by themselves, and we have multiple CPUs, and each one of them are in between. But this is basically the two phases that this guy goes in. So what it does with this address bus, which is a binary bus, it outputs a binary number. And I don't know if I can find my drawing, but it's really... So this is in the book that I wrote, if I can find the drawing. It's out of print. It's out of print. I never did. Because I didn't send in anything for the second edition. It's printed by Prentice Hall. It's called PC for Personal Computers for Technology Students. You might can still get it. It surprises me the stuff you can still get on the internet. But it's got a lot of... So this is the basic makeup of a central processing unit. Now it's a lot more complex than this. Most of your CPUs have two instruction encoders. They refer to them as graphics. So much graphics that they Graphics used to be done all outside the processor. Now the processor does a lot of the graphics for you. Yeah, this is real low. So this is actually showing you some of the processors. This is actually the makeup of an old Pentium 3 processor. This is actually the block diagram. We might get into reactions too on this. So these are the units inside there. It has a graphics unit, instruction encoders. So it's pretty slick. This is not what I wanted to look at. So this is the basic makeup of a computer. So we have the processor, right? Processor. This is predominantly a microprocessor. Then we have a memory. Two types of memory. What's the two types? It's going to be in there. RAM and ROM. Then we have portals. What does the portals allow us to do? Well, the portals allow us to bring information from the outside world into the computer. And the way it is everything in the computer is assigned a binary address. Everything is assigned a binary address. So when the microprocessor wants to communicate with it, first thing it does is it outputs a binary address out its address bus. And all these guys, I don't know if I've got this in here or not. This might not be. Oh, here we go. Data bus control, but this is what I'm talking about. So the microprocessor outputs an address on an address bus, and it's binary, guys. And every box has a circuit out there called an instruction decoder. And so what this instruction decoder is sitting there looking at, it's looking for when its binary combination comes out the address bus. And what happens is that when it sees its address, it opens its door, the mailbox. So in the mailbox system, the mail person is the address decoder. So what does that person do? It picks that letter up, looks at it, sees the address on it. What do? Comes over there, opens up that mailbox, right? You understand? And either what does what? You signal it. You have a flag on the side. What's the flag on there for? To tell the mail person to even stop if they don't have any mail for you, right? So what we have is we have three buses. We have an address bus, we have a control bus, and then we have the data bus. So here's our 3-bit address bus. So how many addresses could we have? 3 bits of binary. Y'all remember how to do that? Take the number of bits and raise it to whatever base you're dealing with. So 2 to the third. What's 2 to the third? 2. We're dealing with 8. Go ahead. You might have did it a little bit in Turbo PLC. I think this, if you took it with me, this is probably the same thing I told you. But once we get the mailbox door open, we have to tell it what we need to do. So here we've got what we call a control bus. And the only thing it says, I'm writing. If it says I'm writing, then the processor will put information on the data bus. And then it says I'm writing, the mailbox knows to do what? Take that binary number off the data bus and put it into the storage. And then the microprocessor puts out another address, and this mailbox would close and another mailbox would open. So technically there can only be one device on the data bus at one time. So even though the data bus is a bidirectional bus, it's what we call half duplex, which means it's 2 directions, but only one device at a time. So the 3 buses that we're going to have is the data bus, the address bus, and the control bus. And that's as simple as you. The address buses now are used. The data buses now are used. Most processors are 64-bit processors, but they run 128-bit data buses. And why? Because they prefetch information. And that's what the cache is in there for. The cache is in there is it prefetch. So the processor's constantly loading up the caches. So normally when we talk about it's a 64-bit processor, we're talking about the size of the data that it handles any one time. So that's 64 bits. So we started off with 4, then we went to 8, then we went to 16, then we went to 32, then we went to 64 on the data bus. So this would be an example of a write cycle. A read cycle. So write means I'm putting information into memory. Read means I'm taking information out. So the control bus, all it's doing in this situation is just telling these devices out there whether to take data off the data bus and to store it, or to take data out of its storage location and put it there. That make sense? So the address bus is used to select. The data bus is where the communication actually takes place. And then the control bus actually controls the communication between the selected device and the processor. And there's a lot of control, guys, that we're not even think about. This just gives you a little idea of what's going on. Billions of times, or millions of times a second. The first processor we had, the first 88, the 88 microprocessor that they originally put in the IBM computer was running at 1 megahertz. And now we got them running well over 2 gigahertz with the data, with the memory. There's some neat stuff they're doing. But this is my drawing, by the way. So what do we use output? So all your input ports have addresses, and y'all familiar with that, but you think you're familiar with it, but you're not. These are physical addresses. These addresses off the address bus cannot be changed. Because if you change an address, the operating system would not know where your input port's at. And this is one reason why Apple computers and IBM computers or compatible computers are totally different, because they don't use the same addresses. So if you bought a video card for the Apple computer, it would not work in an IBM machine or compatible, because they're at different addresses. And so what we have is what we call an address map that gives us this information. So we can literally still see this on a computer. It's a little easier to find on these guys. So here we're going to go to. No, I don't want to do that. I'm going to go up here, go to all programs, and then I'll go to accessories, and then I'm going to go to, system tools, and I'm going to go to system information. I don't think, here we go. So here's the addresses for the input ports on this computer. So if I went to any computer over there, or any of these computers over here that's running a Windows operating system, that's a compatible computer, if I was to look up the I/O, it would be exactly the same. Now these are binary addresses, but to make it easy for us, they're used what base? First age. Hexadecimal. So it says the system timer is in here is between address 0 and 40. Let's see if we get some more. The direct memory access controller, which is controlling the refreshing the memory, it's from 8F 80 to 8F. Now it displays them in the same format. Basically, these machines use 16 bits to address I/O, which gives us the ability to have 65,536 ports. And they have not needed more addresses. I mean, you can't imagine having 65,536 ports inside a computer, right? This is the memory. This is the memory addresses. So even your graphics card. So here's a high definition graphics card. It's got a ton of memory in it. So it goes all the way from F00000 to F03FFFFFF. If we took 3FFFFF and converted that to decimal, we would see that's a lot of memory. So video requires a lot of memory. And this is in the video controller. What they decided to do a long time ago is to handle some of the graphics that you want, is they actually share memory with your applications. They have the graphics have the ability, they have dedicated memory, then they can actually get to your RAM in your machine. So you need to be careful with using these extremely high resolutions because it might cause your computer to slow down a lot because there's not enough room in your memory to hold an application. Then the thing switches into something we call virtual memory, which you don't want it to use virtual memory. That's when it starts going to your hard drive. It stores stuff it's not using on your hard drive or your mass storage device, and then when you need it, it pulls it back off, and it really slows your machine down. And people use resolutions that even the human eye can't even see. So we can do 2048 by something graphics, and you can't even, your eyes won't even pick up that, but it eats up a ton of memory. So there's a lot of things people look at, they buy it just because it sounds good, and then they never use that feature. So they'll go out and buy an iPhone with 32 gigabytes of memory on it, and they use it for Facebook. Oh yeah, 4K, yeah, 4K, yeah. And the Sony came out with one where they added a fourth color. They added yellow to the mix. So they added another in their triad. They went forward, and you still couldn't tell the difference. So I think that didn't last very long. So this would be an example of a machine language program. You can't see them now on the old. They did away with this when they came out with Windows 7. But we used to have a program available to us called Debug. And we could literally dump memory. We could dump the binary contents of memory. Of course, it didn't display it in binary, it displayed it in hexadecimal. But it was really, really cool. We could do assembly language programming. So, but I don't program in machine language. So what does that mean? So it's like the Bible. What was the Bible originally written? Greek, right? Greek. Okay. And then what? But I can buy a Bible written in English. And so what has happened there? Translate. It's just like me. I could go, like when I said we was Iran, what did we carry around with us? Because I never knew what the guy was telling us. He might have said, these are these crazy Americans, or he might have been saying something bad about them. But anyway, so we had a translator that we carried around everywhere we went. Everywhere we went, we had a translator. In Germany, there was tons of people. I mean, every place we went, there was somebody that spoke English. So, but over there, English is basically a second language. In fact, the schools, all the Siebel schools are taught in English. So even when they come into those schools, they have to be able to speak English to be able to take any Siebel schools, which is pretty good. Huh?
Should be required here.
Yeah, I agree. I agree with you. And I think.
If you ask a German, they'll say German is dead language. They'll say not aware.
If you ask the Germans are. Here you need to learn Spanish. If you lived in Germany, you probably need to learn German. Because we did run into one, but that was somebody they brought up front. In all the hotels, everything we went into, all the restaurants, every restaurant we went into over there, the waiters understood English. They talked. So what they did after this, guys, is they came out with a language called assembly language, which we don't really use much anymore. This is very, very complicated. And what you would do is you would have these little mnemonics that you would come in that represent each instruction. You still had to understand the internal works of the processor, all the registers in there. We talked a little bit about registers in microprocessor and intro to PLCs. You had to know every register because you are in control of the system. But what had happened is this guy right here could not, the microprocessor still couldn't run this. So we would run it through a program we called an assembler, which would take this and convert it over to the operational codes, and then it would store the operational codes in there. So this was the first thing, which is still around a little bit, but we don't use that much anymore. So what we went to is we went to what we call high-level languages. These are languages that are written, and of course I need to add to this. This was pretty a long ago. So what we program is we program in a high-level language, and the level that we're going to program with is we call it ladder. And of course, there's like 4 different languages, and I'll try to introduce you to some of those that you might run into in program PLCs. Those PLCs are computers. And what that means is some of the people that come in and get into PLCs did not come up through an electrical background. So they have no idea what a relay is. They have no idea what relay logic is. So if you came up through computer science, you learn programming like you learn Java, you learn programming language for the internet called Java. You learn programming language called Pascal, C++. Those are text-based languages. So the PLC has a text-based language. They call it script text language, which is basically just a variation of Pascal. So that means that gives these people a path. If they understand that, they give them the ability to program a PLC. Then you have people that come up through electronics and they understand logic. They understand and logic, or logic, and that kind of stuff. So we have the ability to program it in where we use blocks that represents ands, ors, nands, nors, and nots. We just pull a block up that do an and, right? You understand? And of course, still the predominant language here is ladder. So I'll show you all those languages. So PLCs, we have about 4 different languages we can program those in. But what you do is you have to run them through a translator. So what happens when you download it to that PLC, it goes to the what? It goes to a translator. The PLC never sees your program. It never sees your high-level program. It is what? It's translated. Does that make sense? So these are just some basic, was the original language, high-level language that I learned. Huh? Visual Basic, it just added graphics to it. So originally, the original Basic was just all script. You typed in everything. You learned all these commands. And you'd say like print. If you wanted something to go to the screen, you'd start off print. And you'd say what you wanted to print to the screen. And it was nothing but text. And most of your PLCs still use that. So a lot of your PLCs still use ASCII to send information because it's so simple, right? You understand? You can do a lot of stuff with ASCII. Visual Basic added the ability to put windows, or put these little windows or pop-ups up on the screen, and actually specify your background color and foreground color. And then you would use your basic program to write what you wanted to do inside that window, which is pretty nice. So Visual Basic, so I wrote quite a few programs with Visual Basic. Played around with Pascal. Pascal and Fortran. Fortran was basically a scientific notation. COBOL was business. So this was the big problem when we had the two, when we was going the Millennium Scare. I don't know, some of y'all, when we were going from 1999 over to 2000, is COBOL. Well, most people that wrote COBOL, when they put the years and everything into their COBOL program, they only used 2 letters or 2 digits, because that's the way most of us enter calendar days. We enter, like when I say my birthday, we get problems now because I say 2551. Well, we're not even by now. People say we're not even in 2000. I was born in 1951. See, COBOL, when COBOL was written, just about all the programs use those 2 digits. And here, to keep up with all this different stuff, like insurance and scales and all this other kind of stuff. So they had a big scare. So they had people out there that had to go back into all these programs that was running COBOL and switch from a 2-digit year up to a what? 4-digit year. So I had to recompile every program. And now the programs took up so much space. So you think about an insurance company that's got 1 million customers, and you go over there and you add 2 more bytes of information into that, right? And they thought airplanes were going to crash. They thought everything was going to happen. Of course, nothing happened. People went out and bought all type of groceries because they thought the grocery stores couldn't work anymore. So that was a big scare. So COBOL was a business-oriented language. So when we first started here, that was the language that all the programs were written here. Pascal, of course, is still out there, and then Fortran. C, we have C and we have C++, which is probably the main programming languages that computer science teaches. And Java. Java is a language that Microsoft originally called it ActiveX. But it's a way you can write programs that run off a website. So instead of just throwing visual information up there now, you can actually develop forms for people to enter information into forms. You can do all kinds of stuff on there now. Graphics, you can download movies and display movies that we didn't have the ability to do. So we have two types. So when I played around with RS Logix over there, Logic Pro, it ran an interpreter. So what an interpreter does is it does on-the-fly translation. So it never actually develops a machine language program. What it does, it translates, brings in a machine code, we use it, and then it's gone. So interpreters never translate. So this would be like when we was over in Iran, that was an interpreter. It never generated a true language, English text, right, or anything. It did it on the fly, and that's what an interpreter is. Then the next thing we do is have a compiler. So that's what the Bible is. The Bible is usually compiled. So what do they do on that? They take the original Greek and do what? They totally translate it over to English. And now I have an English version that I can read. And I don't have to have my translator anymore. Right? You understand? And so they've retranslated. How many languages has the Bible been translated in? I have no idea. And not only in English, it's also been retranslated into different versions of English. So originally we had what they call the King James Version with all the D's and the vowels and all that kind of stuff on there, right? And now we have the New International. We have all these different versions out there that makes it easy for us to read. So a compiler, so that's what we're doing. So up in the screen, when we go, they literally on the Siemens, they call it compile. They say compile the program. So what we're doing is we're taking that high-level language program. And what's nice about a high-level language program, of course, you still have the source code, right? You still have your source code. And when we download it or when we upload it from the PLC, it takes that binary program from the PLC and compiles it over to what? Over to our high-level language. So we can upload or download into the PLC. Right? Everybody okay? So download means what? Send it to the PLC, and upload means, and it's opposite from the internet, and that's what gets people confused. Every time. Every time you make any changes to a program, you're going to have to recompile. Right? And that's what you do. That's what you're doing. So I think, and what we can do is we can compile it to check for errors. So Siemens lets you do that. You can compile it before you download it. You can actually check the program. They show you what line, where the errors are. You can change them before you send them to the PLC. But it also does it when you send it to the PLC. So it's just double check, right? And we'll show you how to do that too. So we okay? So that's what it's going to say. It says compile. Okay. So a compiler is going to completely convert it over. So we end up with two versions of the program. We end up with what we call the source code, which is the original program, and then we end up with the machine code, which is the program that we're going to send to our PLC. So this is why these PLCs don't have to have much memory. The PLCs that we're dealing with, it's got 100K. But they don't need a lot of memory because they just deal with binary. They don't deal with graphics, right? You understand? And they don't deal with multitasking. So on these computers right here, I can bring in all these programs and have them running at the same time. And that's called multitasking. Multitasking means, but it's sharing the time between the processors. So this is why the more applications you have running in your background on your phone, the application you have in the front starts doing what? slowing down because it can only do so much, right? You understand? Because it's a timeshare. So these two programs are not literally running at the same time. So what's happening is the processor doing what? Going back and forth between. So I do that all the time if I'm playing a game on my phone. I don't play many, but if it slows down, I just do what? I bring up and just close down the other applications. Yeah, I just get rid of them. I close them out. Then your phone starts working okay. And these machines are the same way. In fact, if these machines start running out of memory, they start swapping information off your hard drive. So when they run out of RAM, they really, really, really slow down. They really slow down. So this would be an example of a compiler. Everybody okay on those now? That makes sense. So PLCs run compilers. That's not true. Some of them allow you to, if you have a simulator that you can run. Siemens has a simulator on S7 that you can run without downloading the program. And that's a translator, right? You understand? So you never send it, you never compile it, you just bring up the translator and you run, and it brings up inputs, outputs, and you just click little buttons to see if your program's going to run okay. So some of your high-level operating systems, or not operating systems, programming applications support both translators and interpreters. It's just that when you send, compilers and interpreters. So if you can run a simulator, right, without downloading it to your PLC, it means that's going to be interpreted, right? Of course, it's translated, it's transparent for you. Are we okay? Y'all need to take a break. Let's take a 10-minute break. Okay, addresses inside the computer. These are what we refer to as physical addresses. You cannot change these. These are built into the computer, like the MAC address that we haven't got to yet. It's the physical address. The physical address. You do not change them. If you change them, the operating system wouldn't know what the heck things were at, right? That it really, really needs to get to. So all the critical resources that has to boot the computer and get it assigned is going to have a physical address. So the USB port has an address. Well, when I plug a USB slot in that, it's going to automatically be assigned what we call a logical address. What was one of the neatest things that they came up with for these computers, what we call PNP, plug and play. When we put a new like a new serial card into the computer, you had to assign it a physical address. So it came, you had addresses that were available for those ports. And so and I wish I had some of these. So the cards had little dip switches on them that you'd literally have to go in and flip them. And before you plugged it in there, if you didn't do that, and you would come in and plug it in there, you'd have two devices at the same address, and neither one of them. We called it an address conflict. And we still get that problem. I think when I bring up my COM ports on my computer, when I plug this thing in, it says I got a conflict on there because the address that I assigned it is already being used. And so I'd have to be able to go in and find an available address. But logical addresses are assignable, right? You understand that? So when I come in on an Allen Bradley PLC and I assign this IO port bit 1, it's got a physical address which I don't need to know. So what do we assign it? When I say we use logical addresses, right? So anything that I can move around, we call those logical addresses. Anything that I can assign. That makes sense? Huh? Well, the problem is we've always had problems with you're writing information to RAM, and it's a serial. USB is universal serial bus. So you've got bytes of memory inside your USB port, but you're not putting it in there as a byte. You're putting it in there one bit at a time. So you're in here somewhere within that thing right here, and you jerk that thing out, and it didn't even finish the byte up. Now you got corrupted information inside your USB, right? You understand? So that's why they want you to safely remove it. So what that does, it basically just closes it out and makes sure there's no data being written or read. Or even if you If you're loading an application off a USB drive, which we do a lot, now we can get them. And you pull that sucker out and it brings in a bad bit. Well, now the opcode might be telling it to go out and wipe out your whole hard drive, right? You understand that? Because an opcode, just about every binary combination that you have is a valid operational code. And all it takes is one bit in that thing to change, and what you've done is you've changed the processor you told the processor to do something different. So that's why you need to be pretty cognitive of shutting that, unless you know nothing's going on. I pull them out too if I know I'm not doing what. If I'm not reading or I'm not writing, then it's not being used anyway. It's just that you got to be careful because these things use a type of memory that you can read from fairly fast, but it takes a long time to write. Have you ever noticed that? So when you're copying stuff to them, it takes a long time. The problem is that you say something out there and you think it's through, and it's what? It's not through. And that's good that bar pops up there and it shows you the progress. So you need to get used to shutting things down. Encryption is exactly what it means. It depends on the encryption level. The encryption level is a method where we can set up a code and you send it one time between the transmitter and receiver, and it sets up a translator that translates information. So the IBM right now is using what they call 128-bit encryption. So that would mean there would be 2 to the 128 different codes that an application would have to figure out before they could get into your program and use the same code to encrypt your data or decrypt your data. So that encryption is, you can tell when you're using encryption on websites. So by the way, if you're on a website, you can tell one that uses encryption because it starts off HTTPS, which means it's a secure flight. If it just says HTTP, that's an unsecured network. So don't do any money or anything on that. So make sure it's an HTTP, and it's not guaranteed, even that's not guaranteed, but HTTPS is secured or encrypted something. Yeah, it's that one instant at a time. You come up here and you say, I need a code, you get that code, and then from then on, just that one. So they would have to be on there when you initially establish that communication. Somebody would have to be there asking for that code at exactly the same time, which is basically astronomical. I think the only people that can really do that is the U.S. government has the ability to capture information. So they can pretty much see everything that's moving across the internet, even though it's binary. So to me, it wouldn't make any. Originally, when cell phones came out, they were not encrypted. We used to pick them up on the police scanners. We could hear people's conversations on the police scanner, but now it's encrypted. So your data, when you establish that, I don't know if they use 128-bit encryption. Suppose that we're the only company and our allies are the only place that the U.S. gives that ability to. They give that ability under 28. And they don't give that to everybody. So that's one of ours. So good questions. So this is something called Device Manager. And so everything, and these are physical addresses. So if I go down to the USB ports and I look at the port itself, we look at resources, and this is the physical address that USB port is. Now, when I plug a USB card in here, we can put up to 250 devices up to one of these ports. A lot of people don't do that. A lot of people think, well, I've run out of ports, but you can go to Best Buy and buy a hub, a little USB hub, plug into one port, and what happens is they got to have an address, but those are logical addresses. So when you plug it in, it says, hey, I'm out here. And then your computer assigns it a logical address, and that way you can communicate with all these different devices. So logical addresses mean they can be changed. Those are changed by the user. Okay. So to communicate with anything, it's just like the phone system, right? We got to know a lot. So we don't even use phone numbers anymore. How many of y'all know all the phone numbers in your contact list? So what do you use? You use a name, right? And so, but it's got to be but when it dials, it don't dial the name, it dials the what? It dials the number. So we used to use phone books all the time. we needed to know somebody's number, we would find their names. They were all in alphabetical order, and we'd look it up in the phone book. Phone books were about that big, and they were just for you. Yeah, now there's nothing but yellow pages, and then have phone numbers of the companies that are in their yellow pages. So that's about the only thing that's in the phone book, because we use translate. We use logical addresses. So I use names instead of what? Phone numbers. Which is pretty neat. We'll talk about that too. So I can't change the addresses on these PLCs. I can't change they're not technically logical addresses, but they're not the real binary address, right? So we say input, and then we say module 1, right? You understand? And we put a slash, and then we put a bit. Yeah, but it will always be that. The 314, you can assign those. You have to do it in ranges, but you can assign them anywhere. You can put them anywhere you want. So on those PLCs, the actually what we communicate with is assigned by us. We assign the ranges. So by default, they're up at 255 or 254 or something like that. Real weird. But these guys are fixed, right? Now, if I put an adapter card on this thing that has additional ports, then I can set the range. So on these guys, it's not so on a modular PLC where you come in and you put it into a module. Into a rack. Then each rack is assigned a module number, right? You understand? So the CPU is 0. The one next to it is what? 1, 2, 3, 4, 5, 6. How many slots you have? On these guys, we put a module on it, and we say, okay, I want this to be module 8. And it's module 8. So those are definitely logical addresses, right? And then once we assign the module number, then the bits are fixed for us. We can't change the bit numbers, but we can change the module numbers even on the 1214s that we're using. So if we come over here and look and if it don't give a resources, that means these are all logically assigned, which means they have the ability to move around, and then the operating system keeps up with where they're at, right? Now the problem is we have, so what's a driver? So we have machine load code programs. Have y'all seen that before? When you plug something in, it says loading the driver. What is a driver? So a driver is a machine language program that is written to control a certain device, period. That's all it is. Your operating system is nothing but thousands of drivers. It is a machine language program that is written to control a certain device. So everything I have in my computer requires a driver. If my computer don't support that driver, we have the ability to do what? Load them in, right? You understand that? Have you ever plugged anything to your USB and so what's nice about USB, it's plug and play. Most of the time they put the driver inside the little stick in there. So it has its driver in there. A lot of the USB devices, the driver is built into the device and it loads in only when you do what? So what is an operating system? An operating system is nothing but thousands of drivers. That's all it is. But your operating system cannot support every device that you might hook up to it. How many different devices can you hook up to a USB port? A lot. So your operating system has no idea what you do that, so these guys contain their own driver. Or you've got a disk that comes with the device. I don't know if you've ever bought something that comes with a little disk that you have to put the disk in there and install the driver before it works. A lot of applications that are written to support certain things. So I go out and buy a new camera and I want to dump it and control it. Then you have you installed it off a CD, and not only does it install the application, it also installs the what? The driver, so you can access the features of that new digital camera that you got. And then what we have on this guy is we have one program that allows us to control all those drivers. We call it the shell. So you're looking at the shell. This is the shell right here. It's called Explorer. So what it does, it allows me to control the drivers. So I can send things to the display. So if I have an application, so applications usually don't have drivers in them. Applications usually just use the drivers that are available to your operating system. So if your game wants to send something to the video, it don't have the drivers for the video. It uses the drivers that's already there, right? Understand that? So operating systems, nothing but drivers. And then we have one that these guys, we call a shell. That's what I'm using right now. I'm using the shell. It's called, Windows calls their Shell Explorer. I don't know what. So when we install operating systems on our iPhone, that basically you're getting the shell. You're not only getting a lot of drivers, you're also getting the shell that comes along with it. And we have 3 predominant operating systems that we use in our cell phones. Anybody know what the 3 are? Android, iPhone, and Windows. There's still some there's a Windows as an operating system too, for iPhone. So we get a little feel so we understand the difference between logical addresses and physical addresses. So physical addresses we can't change, right? Logical addresses we can reassign. So if we're going to put something into this computer, as part of the main portion of it, it's not going to have a logical address, it's going to have a physical address. So a long time ago, when they first decided to come out with networking they knew was going to be part of the main units of the computer. Originally it was a network card, so we had to buy a card and plug it in there. But over time it's actually integrated into the chipsets that run your computer. And it has a physical address. What do we call the physical address of the network card? Anybody know? It's called a media access control address, or it's referred to as the MAC address. Now on here we can see it. There's a DOS-based application that's been around for years. It's called Command Prompt, and it's still there. It's even there on Windows 10. The problem is that the main protocols that we use to send information on an Ethernet network, you control it through DOS. You control it through the old text commands. So that's why to control the TCP/IP network, you need to have those commands. So those are still not good. So this is what we used to look at when we loaded in our operating system. This is what we saw. We saw just a black screen with a little blinking light called a cursor. I guess it got that name because you cursed it a lot, right? And what's it waiting on? It's waiting on text commands. So the original DOS, you had to learn hundreds of commands to tell it what you wanted, the operating system to tell it what you do. Now we have what we call a graphical user interface, or a GUI interface, which we use icons all the time. And instead of us typing in what we want our operating system to do, we just do what? Point and click. So there's a lot of neat things. One of the things that we use a lot is called ipconfig. And what this does is it tells you the configuration of the IPs and also the network. And what I'm going to do right now is I'm going to tell it to show me everything that's on here. And one of the things it's going to show me, let's spell it right, Rick, is it tells me everything about the network. And one thing it tells me is it tells me the MAC addresses of the different network devices on this computer. So Bluetooth is considered to be a network device. So all your Bluetooth ports in your computer has a MAC address. Now, when you connect to it on Bluetooth, it gets a logical address, right? So you can connect on computers. You can connect a lot of Bluetooth devices to your computer at the same time. But each one of them gets their own logical address that's assigned when you connect it. So the MAC address is a 48-bit number. And I forgot how to make this bigger, guys. Can y'all see it? And they display it in hexadecimal for obvious reasons. And they split it up either by dots or dashes. The first 24 bits, which would be these guys right here, this is what we call the manufacturer's code. So every time if I was going to manufacture a network interface device or a Bluetooth port, then I would get a 24-bit code. And then I get 24 bits to assign to my devices. So how many devices could we have under one manufacturer code? 2 to the 24th. So 2, where's my raised to here? Why is it X, guys? Right here. So 2 to the 24th means I could have this right here. 16,777,216 devices. If I run out of that, then I would get assigned another code by the, I forgot who signs it now. I think IEEE assigns. No, IEEE, I think assigns that. Or okay, does that make sense? So you can go to your iPhone and you can go in and you can look at the information on your iPhone, and a lot of times it'll tell you the what? It'll tell you the MAC address of your iPhone. And that stays with your iPhone. You can't change that MAC address. You can change your phone number, right? You understand, but you can't change the what? The MAC address. So this is every network card. This is true. So every device, it would have a unique MAC address. Everybody okay? Now, what they decided to do, and this was originally what we used when we networked together. We'd come in and we'd network computers together, and they would just use MAC addresses, which is very complicated because we had to understand the MAC address for every device, right? You understand? Which is still available. So you can see I have quite a few. So they came out with different protocols. IBM first came out with a protocol to address computers, moving away from MAC addresses to logical addresses. They came up with something called NetBEUI, which is, I'd have to go back and look that up. But what it did, it allows us to change, it allowed us to assign a computer a name instead of use address computers by names instead of by MAC addresses. And what would happen is automatically when we set up what we call a peer-to-peer server, a peer-to-peer server means a peer-to-peer network means you have no true servers. Every computer can act like a server and every computer can act like a client. We call these peer-to-peer networks. So we use that a lot. So I can share stuff off my computer without, and that would be a peer, right? So mine's acting like a file server, even though itself it's not. And just your Windows supports all that now. But what would happen is one of the computers would elect itself to be what they call a Win server. And what the Win server would do, it would go out there and get all the MAC addresses from all the computers that's attached to it, and then it would match it to a name, so it acted like a phone book. So now I would go up there and I would type in a name, and it would automatically, if it saw a name, it would automatically send it to the Win server, and the Win server would actually find out what MAC address that network card actually belongs to. So this is what we used first. So we had local networks. We didn't have the internet. We had local networks. So we had 3 competing. We had Windows, which used NetBEUI. Then we had another one called Novell, which was a networking. It was a server client network. So you had one computer that was dedicated as a server, and then we had another one called Novell was the big one. So that's what we went to first. We went to a Novell network, but it still wasn't for a wide area network. It was still local, right? It was still networking computers here. So we had a network set up. We set up a network up in our program before about the same time that college did. And I can't think of any other one. Now each one of them used a different addressing scheme, logical. So it allowed us to use logical addresses, but each one of them was different. So it means they wasn't compatible. So it means I couldn't run a Windows network and a Novell network at the same time. So the original server that we first set up was a Novell server. And the college original they set up was a Novell server. Now, what happened was that the U.S. government decided they needed to try to set up a way that we could connect over long distances. And I can't remember who actually set it up, but they decided to use what they call so what's a protocol, by the way? A protocol is an agreed upon way of doing things. And so if I'm going to transmit data, and so what we do is we take the data and we split it up into packets. So if I'm sending data, I don't get control of the network all the time. I send a packet. And what goes inside that packet would have to be, when I put it in that packet, the computer that receives it would have to understand the way that packet was put together. So packets basically consist of three parts. They consist of, this is not what you need to know, it consists of what we call a header, which will contain all your addressing information. And then it has the data that we're actually seeing, and then it has a trailer on it that basically has all your error checking information out there. How to check to make sure that the packet you sent was the packet that was received. Right? Does that make sense? So that's the way we put the data together. Then they had to come up with an addressing scheme. So how do we address the computers on the network without having to deal with MAC addresses? So they came up with a transport protocol, which is how the packets that are put together. It's called transfer TCP, transfer control. I can't remember. I'll look it up, guys. But the TCP protocol is how they put the packets together, and the logical address, and they call it the Internet Protocol, which was the IP address. Are we okay so far? Any questions on this? So what we're going to look at is we're going to look at this IP protocol, which we call an IP address. Originally, when they came out with this, they decided for it to be a 32-bit number. So think about the number of MAC addresses we have available. When we run out of that, I don't know what they're going to do. But that is 2 to the 48th different devices we can have out there. Okay. So because if I run out of my node IDs, I can get another manufacturer IDs. So that would be 2 to the 48th. So this would be 2 raised to the 48th. So this is the number of MAC addresses that we have available to us. Right? And we're still well within those limits. When they came out with the IP address, they decided to use a 32-bit number. So that means we would have the ability to do 2 to the 32nd different addresses, which seems like a lot. So that's how many IP addresses we could have when we got up to version 4. So the only version that I know of is what we call V4, IPv4, which is version 4. And this is when they went to the 32-bit number. But we don't get access to all these. We have dedicated IPs. So the government's got their dedicated IPs that nobody else can use these. Right? You understand? Then we have military have dedicated IPs. We have dedicated IPs for different devices on the network and gateways and stuff like that. They're always at a same IP address. So this stripped it down a lot. But what they decided to do was, instead of trying to do it as binary, that would be very complicated, right? That would be 6 bytes of information. 4 bytes of information. They decided to split it and do it in decimal. And what they would do is, so using 8 bits of binary, the biggest thing, the smallest number I could represent would be 0, and the maximum number I could represent would be 255. So what they did is they decided to break this down into bytes, and then they decided to separate the bytes with periods. And then they decided to do decimal. For me to enter decimal, now it's translated, right, instead of using binary. So I might have a IP address that looks like one dot, right, 168.52.5. We call it a dotty quad, and that's an IP address. These are logical addresses. You know, we assign those, or we could assign them, but we can set it up 2 different ways, and we'll look at that. Everybody okay? So now you know what an IP address. All it is a 32-bit binary number. It lets me enter it in decimal instead of what? Binary. But you'll never see an IP address that's over 255. Everybody okay? Makes sense? That's what an IP is. And it's logical. It's totally logical. So that means it's assigned by something. Now, the problem we had was trying to keep up with these IP addresses. So what they did on the network card that's running, once we load in this protocol, TCP/IP, which is used by the internet, and there's also, so once the government set this up and went there, this did away with just about everything except NetBEUI. So NetBEUI is still available if you're running a Windows network, which is what we do. NetBEUI is still there, so we still have a Win server running somewhere. So I can type in names and it don't use IP addresses. It just comes up and just goes and finds it on the Win server. The Wins is still around using the NetBEUI interface. But what has happened is just about Novell, their addressing scheme is gone. We don't find any Novell servers anymore. They're gone. And the other one that I can't think of is gone because TCP/IP is the predominant transport suite right now. TCP, Transmission Control Protocol, is the predominant way of putting packets together. And then IP is the predominant method of logically addressing any node on the network. So we call them nodes. Anything that needs an address, we call it a node. Everybody okay? Now an IP address consists of two parts. So what we can do now is we can set up smaller networks that we refer to as subnets. So now I can take one network that everybody was trying to look. So on internet, we have one device that can be on the network at one time. So you got 5,000 computers out there, and you don't have the ability to subdivide it down into smaller networks that we call subnets. And then I can use a device called a router that basically allows us, if I'm on my subnet, then I'm only sharing my network with other computers on my subnet. If I ask for an IP that's on another subnet, the router will route it through. So that's what a router does. A router is what we use to divide a network into subnets. So it's got a way to figure out, okay, is this computer in this subnet or is this computer in another subnet? So what we do is we use something called a subnet mask. Now what the subnet mask does is it indicates what port. So what we do is we divide the IP address in two components. From the most significant moving toward the least significant, this is called the network ID. So this would be the subnet, right? So every computer on my subnet would have the same network ID. Another computer on another subnet would have a different network ID. Right, and that's what the router knows. The router knows it knows what subnet each one of these things got. Now, starting with the least significant byte, moving toward the most significant byte, this is the node ID. Now, to differentiate where that's at, we use something called a subnet mask. So the subnet mask starts with ones, and we keep going with ones until I get down to where I want so the ones indicate it's the network ID, and zeros indicates it's the node ID. So if I come up here and I say 255.255, so you gotta use solid ones. This is pretty easy. And then I put .0.0. It means I could have 16,576 subnets, and each subnet could have 65,536 computers on it. But all the computers would be on my subnet would have the same subnet ID, right? So what our router does is our router would come in here on these last bits right here, and all it does is look at these bits right here. So right now this would be like 15 subnets. So if I come up and use an IP, I'm not gonna make it up, that came up and did this, this would probably mean, okay, the router would say, okay, this is subnet 0. And if this one was said, it would say, well, this is subnet 2, right? Does that make sense? So when you set up your router, you set up which bits of the actual IP that's within the network ID that tells the router which route to go. That makes sense. So you got to come up with that subnet map. You would have to come up with the subnet maps. If you were going to do this, you were going to set up these IPs, you would have to figure out IPs. You'd have to make sure, you'd have to keep a chart to make sure you did not have two computers on the network that had the same IP. If you did, every time you try to hit it, that box will pop up in the center and say you got an IP conflict. If you ever see that when you're on the internet, you need to call your ISP because somebody stole your IP address, by the way. So they said there's got to be a better way. How can I have an internet service provider that would have to know every IP address that's out there? So they came up with what we call a DHCP server, Dynamic Host Configuration Protocol. Configuration. So we call these guys DHCP servers. So what happens when these network cards run in the TCP/IP protocol suite? If you have it set up for what we call, so we have two ways we can set up the IP. We have dynamic and we have static. Static, you are responsible for everything. You're responsible for the IP, you're responsible for managing your IPs on your network, and you're responsible for trying to figure out what your subnet mask will be. What we do if we run in DHCP, if we set it up for dynamic IPs, then what happens is as soon as this guy comes online, it sends out a packet saying, I'm looking for a DHCP server. The DHCP server would grab this information, it would grab the MAC address that's part of the IP. It would say, okay, do I have an IP address that's free? Then it will do what? It'll send that IP address into your computer along with the subnet mask that identifies what route you're on, and it automatically configures your IP protocol. So most of your PLCs guys, these guys use dynamic IPs. You can't usually change them because they have no idea where you're at, right? You understand? And we'll show you how to do that. So the first thing I'm gonna have to do is establish the IP address on this because I'm communicating through Ethernet. I'm using TCP. I'm using IP, but we don't use TCP/IP. We're using something called CPS, which is Control Protocol System or something like that. So its packets are put together to run machines, right? It's got a bunch of codes in there that we can use that. But we're still using IP, so that's why they don't call it TCP/IP. Most of the time, the Festo uses Profinet, which is basically, Allen Bradley uses what they call Ethernet IP, which is basically the same thing, it's just under a different name. So they mean the same thing. But they don't use TCP, they use something called CPS, which is packets specifically designed to run machines, and it's an international standard now. So originally when they tried to do this, everybody was doing their own thing, right? You understand? So eventually, if you try to do this, eventually somebody's going to take control of it and says, we need to have a standard. Like when TV first, high definition TV. Why did it take so long for us to get high definition TV? Because we had 4 companies out there that was trying to get their protocol set up as the what? The standard, the international standard. All of them wanted, because the cameras have to run the protocol. Your TVs have to run the protocol. So it took high definition. It was out for quite a while, but nobody could use it because everybody did what? All the 3 companies had their own protocol. Profibus is basically the same. It still uses the CPS protocol, but its address is different. So ours back here, the Amtro line is using Profibus. So its address is different. And the way you set things up, it's not a peer. It's kind of it's not a peer network. It can be. Most of the time we set up one of the PLCs is what they call the master, and all your other computers are the slaves. And then most of your information is kept on the master, and the other guys access it. So Profinet, I think, is set up like that. Ethernet IP, I think, is open. I don't think we use I think it's a peer. So a peer means, well, a peer network means, peer-to-peer means any computer could be a server and everybody's a client, right? A client-server network means you have computers that are dedicated to be servers, and then everybody else would be clients. Normally, we run a combination of both. Most Windows networks is a combination of both. So Windows operating system supports both client-server, and they support both peer-to-peer, which makes it neat. So I can share my printer on this computer. If I had a printer hooked up to it, and then I could say on this computer, I could give the people the rights on who could use that printer. So that means my computer this could be a print server, right? But it's a peer, right? You understand? So it's really neat the way Windows networks are set up. So on here, what we would do, so your PLCs are going to be set up for dynamic IPs. But you have the ability to assign it. So what we do on Allen Bradley software is we have an application called boot DHCP. So what I have to do on this guy, since we're running Ethernet, it don't have an IP address. So the first thing I have to do, so this guy came out and says, okay, where's a DHCP server? And this guy, and I came up here and I load this application in. Oh, it says it's already running, I think. Here we go. And all these guys says, okay, I need an address, and they transmitted it out this guy, and this guy come up here and it popped up the MAC addresses of everything out here on my computer that's looking for an IP address. Now, what I need to know is I need to know the MAC address for this PLC. I know which one it is, it's here, but what we would do is we'd have to go into the setup of the PLC. So let me bring up my camera and see if y'all can see it. Can y'all see that? Okay, that's a lot better, right? So instead on the 1100, instead of using LEDs to indicate your inputs and outputs, they use this display screen right here. So you can see my inputs changing. Can y'all see that? And this indicates the modes we're in. This is the outputs. What I'm going to do is I'm going to come here to escape, and I'm going to come down here to the very bottom, and I'm going to go to advanced. And then I'm going to go to my Ethernet. And I'm going to configure. And this tells me the MAC address right here. So 000F73. And then this is going to be the IP address right here once I assign it to this computer. There's nothing there. So I could not communicate with this computer. So the first thing I need to do on these computers is I need to assign this sucker on an IP. Now, if I was using the DH485, it's built into the machine. This is built into Allen Bradley machines. Here, if I'm using the Ethernet, then it's going to be dynamic IPs. So I have to load in a DHCP server application into my computer and then assign it a MAC. Then I'll assign it the IP address. Everybody okay? Now, what I need to do now is I need to make sure what IP address or subnet my physical network card is on this computer. So here's my network card right here. So this is the wireless. So it says wireless. So here it is right here. So this is my network card. It's my gigabyte network card. So the IP address on this is 192.168.0.100. And it's using a subnet mask of 255.255.255. So that means by George, I'm going to have to assign it the same 192.168.0, and then those last digits are up to me. The last octet over there is up to me. By the way, some people call this a dotted quad. You understand what it's for? So if you hear that term, they call the IP address a dotted quad. So I'm going to come up here and I'll assign it. I just can't assign it 100. If I assigned it 100, I messed up. Now I'm okay because I've only got one computer on this network. The other part is connected to the Wi-Fi, right? You understand? But if I knew the network, I could take this thing and I could hook it up to a switch on Lawson State's network, and I could literally contact and program this thing from my office and my computer, or even home. I could DP into my computer and program this thing from home by connecting it to Ethernet. But I would have to make sure instead of using what we call a private IP. So we have what we call private IPs. Private IPs are IPs that are never intended to go out on the internet. So local networks will use private IPs. So our college uses private IPs. And I'll give you the breakup. So you can look at the first digit and tell exactly if it's a private IP or if it's an internet IP. So that eliminated a bunch of our IP addresses, right? And then we have internet IPs. So you have range of addresses you look at the most significant octet. If you look at that, you could tell if it was an internet IP. So if we tried it, so a gateway will not even let a private IP go out. So what's a gateway, by the way? A gateway is a device that converts protocols. So Ethernet is baseband. The internet is broadband. So I cannot connect this computer to the internet without going through a WAN, without going through a gateway. So you're going to have a gateway. Or if I was to go from a Novell network over to a Windows network, then I could go through a WAN. I could go through a gateway. We could connect them together that way. I couldn't directly connect. So that's all a gateway is. Y'all seen that term, gateway? That's all it is. It's just a protocol converter. So it receives this protocol, converts it back over. What does baseband mean, by the way? Anybody know baseband, brother? Baseband means is we use what we call time domain multiplexing. Basically, multiplexing is when we let multiple devices share the same media we let the multiple devices share the same media. Let's get that over. Baseband, it's not at the same time. So baseband means we only have one device on the network at any one time. So this is baseband. Ethernet is baseband. Now that's no big deal. It's that because right now, am I on the network? Is this computer right here on the network? No, it's connected to the network, but it's not putting any information on the network, and it's not getting any information off the network. Right? You understand? So what this guy uses, Ethernet uses what they call carrier sense multiple access with collision detection. So what your network card does is before it puts a packet on the network, it listens to see if there's anybody on there. If there's somebody on there, it comes back off, generates a random number, comes back on later on and sees if there's anybody on there. If there's nobody on there, then it puts one packet on the network and then it releases the network. If it needs to put another packet, it'll listen. If there's nobody on there, it puts a packet on there. If there's somebody on there, it waits and puts it on there. Sometimes if you're on a long network, two devices put it on at the same time and you'll have a collision and your packet gets garbled. We call that a collision. What happens is both devices will come off the network, they generate a random number, they come on a random time, and odds are they're not going to collide anymore. So that's what it is, carrier sense, multiple access with collision detection. That's baseband. So the more computers you have on the network, the more likelihood you're going to have a collision. And the more likelihood it's going to take you more time to get your packet on the network, right? You understand? So we had called us one day. We had a network card up in the building, up in 200. The guy calls me and says, "You got a network card that's generating packets all the time. I mean, it's just sending out garbage." So we went and disconnected it. So it was bogging down the whole college's network because my computer wanted it what? All the time. Then we have broadband. Broadband, what we do is we modulate the information. So we take it and we place it on a carrier. And then what it does, it lets multiple signals share the bandwidth at the same time. Each one gets less bandwidth, but you're almost guaranteed to have access to it. So the internet is broadband, so everything's modulated, which means it's placed on a carrier. So it means to access, so what do you have at your house if you have internet access coming off your cable? You have something called a modem. Well, what's a modem? A modem's a modulator, right? So it takes that information and modulates it, puts it on a carrier, places it on your cable with all your channels. So all your channels are modulated, right? You understand? And then we have what we call a demodulator, which does what? We call these devices modems. So a modem is what? It's a modulator, demodulator. So it demodulates or brings it back into baseband, right? So baseband is nothing but ones and zeros. It's binary. It's ones and zeros, sent out in a serial string. Modulated, they place it on a carrier. It's really neat. They do different types of encoding, but it's really neat the way they do that. But you can still bog it down because bandwidth is a range of frequencies that a media can reliably pass. So once you get past that bandwidth, then everybody slows down anyway. So even the internet gets quiet every once in a while. Yeah, slow. Like if you get on the internet at 8 o'clock in the morning, odds are it's going to be slow. Most gamers play when? No, they play like 2, 3 o'clock in the morning. Most dedicated gamers play after 12.
Yeah, I play right.
So yeah, they'll be up. They'll be up 2 or 3 o'clock in the, huh? You're not that dedicated, are you? So that's one thing, a gateway. That's why to connect to most of the internet, you usually have to go to a gateway because it's taking baseband and converting it over to broadband and also modulating, right? So gateways are, so y'all know that term now. Y'all know what modulators do, right? It takes the information, places it on something called a carrier. And each carrier is basically different, which would give you the ability to isolate one from the other. It's really neat. So this is baseband. So let's assign this thing an IP. So we know we got to do we know we got to 192.168.0, and then we can make up something. So where's it at? There. So what I'm going to do is I'm just going to double click on the one I want to assign it to, and it asks me an IP address. So there's my MAC address at the top, right? So I'm going to type in 192. I'm going to type in 168. And I'm going to type in 0. And then if you don't enter 3 digits, you need to hit the tab key. Tab key, Rich. And then what do we want to assign it? So let's do 101. But we could have literally used what? Anything there, right? So here I would have to keep up with all my PLCs because if I network my PLCs together, every one of them's got to have their own what? You know, so that was something you're going to have to document. Okay. And what we're waiting for is to come up here and pop up here. So if I go back to the camera, notice it still has zeros out there. But as soon as it pops up here, as soon as it goes back and scans it, it should assign it the IP. So if I needed to assign it another IP, what I'd have to do on this guy is I'd have to unplug it because it's only asked for it once, right? I'd have to unplug it, plug it back in, and then it would come back and it would look for a DHCP server. So we got it. So I'll come up here and look at my IP address. And there it is. So now we got it. See the IP? Can you see the IP in there? So I would have to do that before I could do anything, right? You understand? So I'd have to do that before I could do anything on these computers. So I had to run an application called DHCP, boot IP DHCP. Okay? And I think I even had to do this on Compact Logic, which are their new things. Now let me go. So Siemens has put out something called Total Integrated Automation. What do you think that means? Everything is built in. So we don't have to run a special application to assign an IP. It's built into the TIL port. If we wanted to connect a HMI panel to this, we'd have to get an application that supports an HMI panel. It's built into the TIL port, right? You understand? So it's got a lot of stuff that's built into it that makes it a lot easier, and it's all in one application, so you don't have to get all these different applications. Okay, guys. So I've established my IP, so now I can come in. I'm not going to save the changes. So what do I need to do next if I want to make write a program for this thing? Well, the next thing I got to do is configure the driver. So what we would use for this would we use RSLinx. And up here it says communications. Can y'all see that? And then I would say configure the driver. So now we know what the driver is, right? It's a specific machine learning program that's designed to run something. So these are the drivers we have available. So these are all the drivers. These are all the different ways that I can communicate with an Allen Bradley PLC. So notice I just click on available driver types. Now right now we have 3 drivers running. We have DFI, that's the one we used on some of our computers. But I had to make sure I loaded in Ethernet IP. So if I'm going to communicate with this guy, I had to select the Ethernet IP driver, right? You understand? That makes sense. We can go ahead and stop these other ones. We're not using them. I could uninstall them, but I'd have to install them back for intro to PLCs. So the 504s use this guy right here. They don't use Ethernet. The 1000s use this guy right here. So if you was on one of the, we didn't use any of the 504s. Did I cheat y'all? Yeah, I did. We didn't use any of the 504s. The 1100s, we have an option of using this guy or Ethernet. So I decided to use Ethernet because that's what we're going to use for the Siemens PLC. Are we okay? So we know we're going to have to do that. We know for the Siemens, we're going to have to, it don't come with the IP built into it, right? We're going to have to do what? We're going to have to assign it dynamically. Oh, I needed to show you where you do it on a Windows computer. So you do it in Control Panel. By the way, Control Panel is not visible on Windows 10. Down at the bottom, you just type in Control Panel, it'll pop up. And then we go to Network. And then we go to Adapter Settings. And then these are all the different network cards. So I would go to my local area network. I'm sorry. By the way, these guys, what Windows does, if it does not find a DHCP server, it will assign itself an IP. And it will always be 192.168.0. That's pretty standard. So Windows will have an IP address if you have it set up for dynamic. If you have it set up for static, so we bring this up, then we go to properties. And then we go down to V4, TCP/IP V4 right here. And then properties. And we have this set up, use the following IP. So if I select this, obtain an IP automatically, then this computer would be set up for dynamic IPs. So odds are that's what you got. Because you want dynamic IPs because your internet service provider does not have millions of IPs. So if you looked at your IP address using that config sys, every time you log in, you're going to get a different IP. Because they might have 1 million customers, but they know they might have only 50,000 on any one time. So they might buy 75,000 IPs. And then what do? When you log in, you log off, they give it to somebody else. When you set up your DHCP server, you can set it up to keep a lease. We call it a lease. So you can keep a lease like for 3 weeks. And that way, if your computer's not turned on for 2 weeks, if you log in, you get the same IP. So ours is set up like that because that would be awful if we had a power failure and we come back in and everybody in the whole college got the wrong IP, got a different IP, right? So they lease it. Our DHCP server too. We have DHCP services running on our server. We got our own domain server over here. So What's a domain? So on the internet, the internet domain and a local area network domain are different things. A local area network domain is a group of computers that share the same login security. So what I can do is I can go over there on that domain server and I could change the password for METSTU without going to every computer and changing it, because you're validated through a domain server. It's got a file server on it too. So when you log in, if you ever went down to your devices, you see you would have a logical drive called students. That drive is not on your computer. It's on the domain server. So it's running we got two features, and it's also running DHCP for our network. So it's running multiple servers. Then we have a file server over there. It's strictly what? It's strictly where we save files and move stuff around. So it looks like I got a lot of drives on my computer, but I don't. They're all on the network. And we call it mapping. So before you can map a drive, the computer you're getting it from has to share it, right? Does that make sense? So we've got these shared. So, but when you log into these computers, just look, you'll have a drive it's called students. So here's our PLC manuals. They're up here. So instead of, if we lost the internet and couldn't get on the Blackboard, then you could access them from this section right here too. So this is where you set it up. If you set it to static, guys, you're responsible for everything, right? Not only are you responsible for this, you're responsible for the subnet. If you got to go out on the internet, you got to find out where the gateway is on your network. Gateways, by the way, always will end with 1. So 1 is reserved for gateways. But it's got an IP address out there too, and it's probably going to be static, right? You understand? Because you don't want your gateway doing what? Moving around. So our domain server over there has a static IP because we don't want it doing what? We don't want it moving around. What we're starting to do, guys, the internet is starting to run out of IP addresses. Because you think about the number of IP addresses on the internet now. How many IP addresses do you have? Your cell phone has an IP address, right? You understand that? So every cell phone in your house has an IP address, right? All your computers have IP addresses, right? But the cell phone actually has an internet IP address. Well, that's not true. If you connect to my network, if you connect to a router, it's going to be a private IP. So private IPs are still going to be, not private. Local area networks are still going to be IPv4, because I can have a 192.168 here, and then we can have 192.168 on another private network, right? You understand that? So we don't have to have a lot of private IP addresses because they can be shared over the world. It's the internet addresses that can't be shared. So what they did, they came out with another one called an IPv6. This is what the internet uses. They went over from IPv4 to IPv6 a few years ago. I can't remember. So here's an IPv6 address. There's an IPv6, and they don't show all of it. So what they do is they use hexadecimal. Instead of using bytes, they use words. So that's 16 bits, right? You understand? 16 bits. They separate them by either dashes, but you see them use a colon a lot. It looks like this might be repeated. I'll have to go up and look at this, guys, but this guy is unbelievable. I forgot it's like 128 bits for IP addresses. And this is what the internet uses. But you don't need to know that because you access it. You don't access it through you access it through your gateway, right? You understand that? Your gateway has to keep over it. So your gateways and your routers and your switches, that's what they do. They learn IP addresses. So your gateway learns an IP address. So it goes out there and everybody says, okay, who are you? Who's on my network? You say, okay, this is me. And they say, okay, this IP address is on this route. This IP address is on this subnet, right? You understand that? And then when it goes into the gateway, it'll save yours. It'll say, okay, this packet is coming from this guy, and it'll convert it over. So what these switches and these gateways, these are computers. These are not just boxes. These are computers. They do a lot of stuff. So we got a little feel of this. This makes sense now. So now we should be able to do that. So now I can go into RS links. I got it somewhere. And load the driver. Now once I've loaded the driver, we can verify that we're communicating with the PLC. On RS links. So we can go up here on this little guy right here. Can y'all see the little network icon up there? I'm going to click on that. We'll come down here. And here I am right there. 101. Last time I played around with it, and it keeps up with the last one. So there I am. So I know I've got a connection with my PLC. Are we okay? Makes sense? So we got all that going. So what do we do next? Well, now we're ready. So I'd come up and load in RSLogix. By the way, this is 5000, so I'll show y'all some things about 5000. And now we're ready to go, right? We come up to comms, especially if you have multiple PLCs that you're programming, you've got them networked together. You have to come up here and say who's online. And then you select the PLC that's online, right? Okay. So if I had multiples on the same network, all of the IPs would have popped up, right? And I could have did what? I could select and I could go to any IP, any PLC on the network and change programs, and we can create a new program. What did it do? It automatically uploaded whatever program happened to be in the PLC at the time. You lost all your symbols, so your symbols are not saved with your program when you compile it and send it over. One thing that they did with the TIA portal is your symbols are saved. So if you upload a program, you get all your symbols. We don't call them symbols anymore. We call them tags, by the way. So on RSLogix 500, symbols are optional. From now on, guys, they're not. They're required. Siemens will automatically assign it a tag. 5000 will not let you program without what? With tags. So you'll have to set your tags up. You can either do it on the fly or you can go ahead and set up your tag table. So what we'll do here is we'll show you how to set up a tag table. So it's really good. What's nice about using symbols, and y'all did that in my PLC class, right? What's nice about using those symbols is that you don't have to know addresses. All you need to know is names, right? So that's the same thing with tags. So once you set up, so what you would do is if you design your system, you would come up and you would go ahead and decide what sensor would have what tag, what port would have what tag right off the bat. So most of the time what we'll do is we'll show you how to do it on the fly, which means you go up here and you click and you bring up an input device or stuff and you assign it a tag. I'll show you how to do that not only in the Siemens but also on the 5000. So it lets you do on the fly. Siemens, what it does is it'll assign a tag. It'll call it like tag 1, tag 2, tag 3, and then you go in and you can rename the tag. 5000 will not let you continue until you do what? Until you assign a tag. So what's a tag? It's a name for a port, right? Are we okay? So this is RSLogix 5000. I'm sorry, this is, by the way, RSLogix 5000 is a lot like this. It's got this up here, but you can add, you can do that on here too. You can delete and add on your tables, but we still have to go through all these tabs up here to find what we need, right? This is where we can go and look at our PLC. So this is our properties. We could assign it a password. So if you, in your company, odds are, you probably got, every PLC's probably got a password, but it probably will be the same password for all of the PLCs. And why? So people can't go over there and, it's a good idea. This shows me the path, what we're using, why we're doing that, right? You understand that? So, this is our function files. This is where we can go and configure. What they've done is that back in Intro to PLCs, we use the timers. I mean, sorry, the counters we used in that situation were software counters. So that means when we put that in there, it loaded in a section of machine code that supported your counter. The problem with machine codes, the language is it takes time to run programs. So the big advantage of hardware has over software is hardware has the ability to always be faster. So what was happening was they would take these software counters and they would try to hook them up to encoders, which are the spinning thing that's on motors where they can get the speed and position. And the software counters just couldn't keep up with those things. So what they started to do, guys, is they're starting to put hardware counters, literally circuits inside the PLCs that are hardware, and they call these high-speed counters. So this guy right here's got, I think, 2 high-speed counters. I think the 1200 has 6 high-speed counters. So you don't program those, you configure, right? And you don't have a counter block, you have a counter block to access the accumulator of the counter. And that's software. But, that's not very important. What's really important is to make sure that counter, if I check it every second, the count would still be right, but that counter is not going to mess any counts, right? So on those, to access this, we have a high-speed counter. It's not an instruction. It's an instruction we use to access the accumulator. So this is where we accumulate that. This is where we can set up how we want to, if we want to set up a pulse train. So a lot of devices work off pulse train. This is where we would set up pulse width modulation. We'll set up that. We'll talk about that some too. Pulse width modulation is the preferred method for controlling the speed of DC motors now. And so they do it with pulses. And then the motor averages out. We'll show you how that works too this semester, because that's very important. So we could actually output pulse width modulation directly off this PLC. And some of your variable speed drives, if the variable speed drive runs off a PLC, it sets the speed through pulse width modulation. The pulse width modulation feature is going to be on most PLCs. Now, this PLC can't really do it because it runs relay outputs. We can do it, but it has to be real slow. So we'll try to show you all that. Now, these is where we these is where we configure our interrupts. This is where we configure the LCD panel, HMI, which we don't have. So all this is in what's in the what files? These files are called function files. Right? Now, our main program is called what? Ladder 2. And of course, it shows down here, it shows file 2. Now, what we can also do, I don't know if I showed y'all this, is you have the ability to do what? Rename it. So instead of, if I didn't want it to be called Ladder 2, I could give it a name that's associated with what that program does. Are we okay? So I call it rigs. And notice what? Tab change. Now, the problem we have is that I can get into very complicated programs. I showed y'all the program that runs a module, right? And the longer the program goes, the more complicated it gets to edit it. Not only edit it, to maintain it, and just to keep up what it does. So what most larger programs are is we split them up into individual modules, which we refer to as subroutines. And what we do is a subroutine usually only does one task. So it means if I'm going to extend the cylinder or do something like that, and everything that's involved in that, I might set it up as a what? Or the subroutine. And in that way, if my cylinder doesn't extend, I don't have to find that section inside that big old long program. I can just go to that subroutine that does it. So most large programs are split up into individual small modules that we call subroutines. Now this is real hard to do. First of all, you can't do it if you're in run, so I'm going to go off it. Everybody okay there, right? Right now it's untitled. No, it didn't go offline. No. Okay. We'll create a new file. Oops. There. I couldn't remember how to get it back. So what I'm going to do, what I did is I just came up here on program files and did what? Right click. I'm going to choose what? New. Then it's going to ask me for a number, subroutine number. So this guy here, and it automatically assigned it 3 because the first 3 programs, the first 2 programs are reserved. System 0 and System 1. We can't get into that. Then we have ladder 2. So the first number, the next number is assigned on this one is 3, but you can assign it any number. Makes sense? And then you got to give it a what? A 9. We'll call it 3. And then I'm going to come up and hit this. And what you notice down here, there's another ladder now called what? Ladder 3. And I can bring this up. Now down here on my tabs, I have 2 tabs. One's called ladder 1, one's called ladder 3. This would be considered, so on everything, you're always going to have a main loop or a main program. And the main program somehow is going to call those subroutines. Everybody okay? Everybody make sense? Are we okay? Okay, so what I'm going to do is I'm going to bring up one of the Allen Bradley programs and show y'all the main loop. And this might make sense now. I don't want to get them there. It'll actually load the program if I double click on it because I got RxLogix running in. So. I want to bring up the PDF on that because if I double click on that, that's the actual program. If I double click on that, it will load into RxLogix. And I don't want to do that right now. Oh no, these are the ones that the guys actually wrote, by the way. Oh, here's PDF. So what we're going to pick up is a new instruction. You see what the instruction says? JSR says what? It says jump to file number what? 4. Whatever you assign is file 4. That would cause this to jump to that subject. Right? And you can see basically this is very similar to most of them. Then once it got to that subroutine, so let's go look at the subroutine. This is going to be a little hard because they didn't identify the subroutines. Yeah, here's 3. They did. Here's 3. Here's 4. Not yet, I'm up to 4 yet. So that's subroutine 3 that we're looking at right now. Here's 3. Here's 4. Oh, I'm still got you. I keep saying 4. Here's 3. 3 is the longest one, by the way. Here's 3. Y'all gonna love programming that thing in. So here's 4. So what it's going to do is going to fill some memory. So what it's going to do is going to set all the outputs to 0, which is basically the way the thing is configured, which means everything's going to return to its where from it started. So if we had the rotary robot, if it was over here, if I ran this thing, it would automatically do byte reset. So we're going to have to figure out how to do this. But look at the last instruction in the subroutine. It's called what? Return. What would that cause it to do? Well, it's going to go back to the next rung after that JSR. So automatically it's going to go back into your main program. That makes sense? So if I was having problems with the reset or the interrupts or anything like that, then instead of me trying to find it, I would just go directly into this and see if I could figure out what's going on. By the way, this is one thing that we teach in advanced PLCs, but it's not a hard problem to understand, right? So if I was to go over there on that robot, the FANUC robot that's running the Amatro line, and I was to use that to look at the main program, it's just a bunch of what? Jump subroutine. So it's got a subroutine that picks up the part. It's got a subroutine that places the part. It's got a subroutine that picks up the spring. So if I've got problems with that, instead of me trying to reteach, so we had this problem. When we moved the manufacturing line from this line over to that side, the robot missed the parts because the way the lines they're not connected together, so undoubtedly the floors are not the same. So what did we have to do? We had to reteach the point. But instead of me finding the points, all I did was go into that subroutine. And by the way, if it's not called, it stays in the subroutine. So I could just do what? I could just keep running it until I got the point the way I wanted it. So yeah, I had to reteach everything. But instead of trying to find it, I just went into the what? The subroutine. So look, jump subroutine, jump subroutine, jump subroutine, jump subroutine. So a lot of your main program is just doing what? Jumping out to these subroutines. And it does do some stuff down here at the bottom. In fact, here's where it starts. Uses a lot of memory bits, internal relays, right? It uses a lot of latching and unlatching. We're going to have to learn about that, make sure we understand that. So it does do something. So this, did I go? Now I'm in 3. This is 3. This is 2. So this is where 2 ends. It ends with a jump subroutine. Then it would come in here, and when it hits there, what would it do? Just go back up to the top and just scan like that. So subroutines, if you get out, and I guarantee you, if you get into the PLC programs that are browsers, they're going to have subroutines. Because it just makes it so easier to manage. It makes it so easier to edit. It makes it so easier to troubleshoot because you're not dealing with a PLC program that's got 100 lines. You're only dealing with what? With modules. By the way, we call it structured programming. I used to hate straight line programs. You get into a PLC and they program that thing from top to bottom. And you try to what? Try to find what you need to find. Right? They don't use any symbols. I really love when they went to required instead of optional. Even though on the Siemens it is kind of optional because if you don't give it a tag, it's going to do what? It's going to assign it a tag, but they're going to be numbered in sequence 1, 2, 3, 4, 5, and then you got that still don't make any sense. So, but the 5000, once you select a port, you're going to have to do what? You have to assign it. So we'll try to show you that. So now the program don't look that bad. So if I was having problems with this, then I would know. And so this is what we're going to do, guys. We're going to come in here and we're going to figure out how the Siemens specifies the JSR, jump subroutine. And it's really easy. It's really easy. And then when we assign our tags, we're going to assign it the exact same tags that that Festo uses. So in yellow, this is not a tag, this is a comment. What Siemens, the symbols are in green. So we'll use the what. We'll use exactly the same tags. We do have another little problem in that Allen Bradley's PLC's addresses in words. So what's a byte? Everybody know what's a bit? Bit. What's a bit? One single binary digit, right? What's a nibble? 4. What's a byte? 8. What's a word? 16. What's a double word or a long word? 32. And that's PLCs, that's usually where they give up. These guys support what they call quad words. Allen Bradley moves their modules in words. So that means you could have a module number like this uses module number 1. I'm sorry. Yeah. This uses module number 0, but it could go from 0 to 15. Siemens does theirs in bytes. So every module number or slot number, we could go from 0 to 7. So module 0 would go from 0 to 7, then we'd have to go to 1, and it would go from 0 to 7. So Siemens goes in bytes. Their logical address goes in bytes. And that's a big difference. So what we'll have to do is I'll give you a chart where we're going to transpose these over and figure out what byte level we're going to do with a word level address. We'll go ahead and assign those right off the bat. And we'll go ahead and assign the tags on a chart. That is a big difference, right? Another big difference is that Allen Bradley uses a colon to identify where the type of port we're using. So I means what? Input. And we use a colon to separate it from the word module number. And then we use a slash to separate the bit number. Siemens, and we use O for what? Output. Siemens use Q for output. They don't use O's. They do not have a separator between the module number and the type of port. We say like I0, and the 0 would go right next to it. They separate their bits. They don't use a slash, they use a period. So in Allen Bradley, if we use a period, we identify it as a word. In Siemens, if we use a period, we identify it as a bit. The way we identify words is we identify it with the type of port. So if I put I, that's a what they call a boolean or 1 bit. If I put IB, it's a byte. If I use IW, it's a what? It's a word. If I use IDW, it's a what? A double word. So they don't specify that. They specify that in the instruction itself. So Allen Bradley uses a period. Siemens uses a period to identify the bit, and that's really different between the two PLCs. And it don't use O, so that's something you're going to have to get to identify an output port. It uses what? Q, which I like, because even me, I still accidentally hit O's for Q, so you don't have that problem over here, right? So that's good. So any questions so far? Are you okay? So y'all go ahead and take, I know we only got 45 minutes. So let's see what we need. So gave y'all a little introduction, showed y'all, so let's go back and just review some instruction. Everybody okay on counters? So what does counters need? All right, so we block, so Siemens still uses blocks for counters. Siemens uses, but what was the type counters that y'all remember back from that we could run into in PLC, not just Allen Bradley? Y'all remember that? Cascading is just taking one and feeding it into another. We could have a single input counter, or we could have a double input counter. So on the Allen Bradleys, it becomes enabled when you bring this input right here to it. Siemens used these two input counters. Siemens has up-down counters. So you have up-down counters, but all of them are enabled. We'll have to build around with that, right? Understand that. They still use block counters. The S7 software uses the coil counter. So they're actually usually, when you insert a counter into the diagram, it actually puts the coil down there. And then you have to give it an address, and then you have to put the time and stuff on, I mean, not the count and stuff on there. So, but what they did on the Siemens is they adopted basically kind of like what Allen Bradley uses. They went to the block counters. And what else? I can't remember. This is one of the programs that we did in Intro to PLCs. I don't remember which one it was. Counting a bunch of stuff, though. Wasn't it? Oh, this is what. No, this looks like something we might have did in advanced PLCs in this class. So this is what the TIA portal looks like. And what does TIA stand for? Yeah, so what it is, everything's built into it. We're using version 14. I think they got a 15 out now. This is one we're licensed for. Takes a while to load, right? So what it pops up with right off the bat, over and right in 5000 does this also, but this is the program that you've already been working with, which is pretty neat. So you don't have to try to keep up with where did you store them. They're all stored in a certain location. If you don't store them in the same location, you can always do what? Browse, you know. So here's the actual distribution station that's on here. If I wanted to make a new program, I'd come up and do what? Create. First thing it wants is a what? Okay. Then you can come in and you can change the path if you wanted to. So if you don't want to store it in the default path, you can put it anywhere you want to. Right? You understand? You can also assign the author of the program. Odds are it's going to give the name of whoever signed into the computer, but you can always change that. You can put comments in here, whatever you want. And all you have to do is what? Create. So what didn't I do first? First of all, I didn't run DHCP. I didn't run RS links. Don't why? It's all in here, right? So in the Allen Bradley software, what they do is, so what's the next thing, and we should have done this, I was going to create a new program under Allen Bradley. What's the first thing I would need to do? Yeah, we would have to configure the model number. If we had any other additional ports, additional I/O devices, we would have to come back and add those, right? You understand? So let me bring that back up. Let's go here and go to new. Let's go back to the procedure. Okay, so first thing I need to do is what? Choose my processor. So this is the MicroLogic 1100 version D. Okay. And then what would I need to do? If I had any I/O devices, I would have to come over here on I/O device and do what? Double click on that, and I would have to come in here and add all the devices that this guy supports. And of course, this is I call it a hybrid PLC because it can be used as a fixed PLC. And then it's got this little door on the back, right, on the side, that we can snap off and plug in modules over here. And put it on this rail right here, we call it DIN rail. This is becoming very, very popular for PLC. Instead of having that whole rack or that whole chassis, they come up with a PLC like this, and you just snap it on. So its backplane is actually built into the PLC, right? Makes sense? So here's where we would come in. We would have to know all this information, right? By the way, if I don't know the PLC, usually over on the side there's going to be a label on here that hopefully, if you're going to put modules on there, you write that information down, right? Or you'll have to break it apart. Write that information down so you'll know how to configure it. So here's all the ports I have. This guy looks like it supports up to 4 additional modules. So this is not a very big modular PLC. I call them hybrids because you can use them as a what? A fixed, or you can add modules to them. Okay. Everybody okay? That makes sense. Okay. What's the next thing I would need? Well, we could. First of all, we'd come up here and make sure we go to who's online, and we would make sure we connected. We would connect to that PLC, right? You understand? Okay. So up here, what we're going to do, the first thing it says I need to do is what? Configure the device. I will come up here and click on that. And by the way, TIA Portal itself supports a lot of PLCs. Add a new device. Then what we would see, but this one, since what we did, we got the PLC, we got a unlimited license for the TIA Portal version 14, and we got and for $250. We bought them in what we call 6-pack. So what this guy does, this TIA Portal only supports that PLC. If you went out and bought your $18,000 TIA Portal at your company, then it's going to have a long list of what? PLCs. So I'd come down here and I'd find this model number. Where would the model number be at? So here's all the 1214s available. So what this right here indicates is how we power the PC up. The PLC up. So that means this PLC would plug directly into AC. Then it tells us what our input modules are. So these guys are DC input modules. Input devices. So all my input devices would run off DC, right? And then it says it has a relay output. So the output's a relay. Now what's the advantage of a relay output over other outputs? Everybody know? It don't care if it's AC, it don't care if it's DC, it don't care if it's 120 volts, it don't care if it's 15 volts. So it's more flexible on what type of output devices you're going to run, right? If you got a DC output, by George, you get what DC it is, and the predominant value, guys, is 24 volts in PLC. So we put 24 volts in here on our inputs, right? You understand it's a DC input, right? And it's relay output. So what can I do on that thing? I could turn on a 120 volt relay if I wanted to, right? You understand? We would have to see what the maximum rating. I think these things are rated like 240 volts. What's the big disadvantage of a relay output? I just told you a while ago. Speed. They're not very fast. So I got to energize the coil. The Joel's got to generate a magnetic field. The magnetic field's got to pull the armature. The armature's got to come down and close. Right? You understand? Plus, it's an electromechanical device, which means what? Two things can fail. Right? So relays do have some advantages, but like I said a while ago, I can't use a lot of pulse width modulation on this thing because it's got relay output. And they can't keep up with what? Extremely high frequencies. We're using ours is a DC version C, so it'd be down here DC. And then I would have to know which version it is, right? And where would I find this information? On the label on the side of the filter, right? So don't cover that stuff up, right? I'm going to show you something neat that they've done with this guy. It's really cool. This is the guy we got. Right? So right now I have that PLC. And then if I had modules up to it, I would have to come in and do what? Configure the what? Configure the I/O. Everybody okay? Any questions? But it also has the software that controls the what? The HMI. So we don't have to have a separate application to program an HMI. So hopefully we can get to it in time. Since we got such a small class, we might be able to let y'all play around with HMI. So here's the PLC. We okay? Looks like it's got a little problem. Looks like I gave it the wrong one. It's got 2 Ethernet ports. I was on the other one. So right now, this is the IP that it's got, right? You understand that? So what could I do? Okay, let's just do it here. If it don't, well, I have to find another place. We don't need to add a subnet. Gave it a name. We have the ability to change that name, by the way, so we can have multiple PLCs with different names. Right here, this is device configuration. So this is where we would actually come in and add our different input ports and output ports, right? If we had additional ports. So we're going to do this. We got the 1100s really cheap, but the problem is it didn't have enough digital ports to support Allen Valley. So what we did is we bought a module, an IO module. Some of them these hadn't even been opened yet. This one has. So this is going to have another feature on it that we don't have. Some of y'all don't have. Now this PLC, by default, supports an analog input. And more, we're moving to in automated systems. We need to be able to monitor analog information. But we have what they call this little square in the center right here. When you look at your PLC, this is where we can put signal modules. So we have a analog output module that will snap in there. So our PLC has the ability to analog input and analog output. Are we okay? Don't lose a little this that comes with it. So we can look at the layout of the I/O, and you can see it's got how many inputs? How many? 10. Right, 10. Notice their numbers 0 through 7, and then they start over again with 0 and 1, right? We're okay? See what I'm talking about? Yes or no? And then we look down at the outputs. How many outputs does it have? I don't, really? I don't think it had that many. 12 inputs? Yeah, it's got 10 outputs. I'm sorry, you can actually look at the front, and it's got 12, 8, 9, 14 inputs. 14 inputs. And then if you open up the first door, you look on the right. Let me turn this on the camera. Instead of me saying, do y'all see this? So if it focuses in, so here's our inputs, right? Here's our analog. We have 2 analog inputs. This guy. And what you're going to do is, if you don't have it, we'll come in and we might go ahead and do this. We're going to put an analog output signal board in here. And of course, this is where we would access the actual. This is the terminal board for the analog. And here's the terminal board for the outputs. We got outputs 0 through 7, and then it goes 0, 1, right? You can see how this thing goes into. So this would be addressed as Q0.0. This would be Q0.1. And then we get over here, this would be Q1.0, right? Make sense? Okay. Now the only interface we have for this guy is Ethernet IP, or Profinet. This is Siemens, they call it Profinet. So what we're going to do in this class is we're going to let you actually build the cable. This cable right here is very expensive. We have two types of cables. We use what we call twisted pair cables. This is called a shielded twisted pair. So that's why it's got this big old metal thing on the end. It's an industrial grade cable. So it runs a metal shield up here to help prevent electromagnetism. We're going to use what they call unshielded twisted pair, which is a lot cheaper because we're only going to make them this long, right? You see the problem with this. So by the way, this is it's called an RJ45 connector. It's actually got 8 pins on it, but of the 8, only 4 are being used. We'll show you all that. So some of the network cables you buy, you'll only see 4 wires coming into it, but most of them put all 8 of them in there because that's the way the standard cable comes with 8 connectors. Plus, it gives you more mechanical speed. And you got to be careful. With this little tag, it's kind of like your phone jacks. If you still got phones right at your house. How many of y'all broke those little tabs up here? And then what happened? You pick up your phone and put it down. So most of them try to put a cover on to prevent them from getting caught on stuff because you can't do anything if you break it off. The only thing you got left is to replace the connector. And the problem is that if I do it on this one, I've lost the shield, right? You understand? So I'd have to buy this really expensive connector and figure out. I don't think we got the tools to actually handle the shield and thing. But we did do that in Germany. We did make them. They did have the connectors there. So we made our own cables. Come to think about it. So this would be the information that tells us about the PLC itself. This is not a label on the 12th, and this one, the door has been taken off because some of y'all might have a cover on here, but this is where we're going to put the expansion module on. And this is the expansion module right here that we're going to add. And it adds additional 0 through 7. So it adds an additional 16 inputs and 8 outputs. On the output, this will be the one we do. We'll show you how to do that. It is extremely hard, but you can see this plugs directly into the back plane of this guy, right? And it's going to latch in. It's going to latch in real good. So it's going to be, once we latch it in, once we line it up with the DIN rail and latch it in, if I can do it, you got to push down on it. And then it's connected pretty good. Right? And then this will be mounted on the DIN rail. So this is what we'll end up with for our final system. And then we'll have to assign the we'll have to go into configuration and assign the module number for this guy. By default, it comes up and assigns it A. And I think next time we just left it there. Because it makes it real easy to differentiate going from 0 over to 8, right? So by default, this guy puts it on module 8. This guy's also got a second side on it. On the left-hand side, this is where your additional I/O modules go. On the right-hand side, excuse me. On the left-hand side, this is where you put different type of communication modules on it. So this guy here supports Ethernet. Well, what if we needed to use DH45? Well, we can buy a module for that. So they could communicate on the Allen Bradley network, right? You understand? Also, for current loop, all these different types of interfaces that we have to communicate, we can also put those in here. So on these communication modules on the left, IO modules on the right. And that same thing true on the 314s too, the ones back there. Now when we finally hook these things up, so what we're going to do, the first thing is we're going to go ahead and I want to find computers over here that don't have the TL portal on them, so y'all can see, actually go through the whole installation process and keying and doing the, setting up the software key on there. And then also what we'll do is we have some little switches that we can mount into the inputs, where we can actually play around with them a little bit. And we'll do that first. We'll have to bring some DC power supplies over here because this is a DC, DC, DC. So that means we got to power these things up off 24 volts DC. By the way, on Siemens, let me bring it back up. They refer to the common, what we call the plus. Let's call it the plus. They refer to the plus as L. So if we look right here, down here where the power is, they refer to the plus as L, and the minus they refer to as M. That makes sense? If it don't, that's just what you got to use to. And they use normally we use brown for plus, and they use blue for minus. So that's opposite of what we do. Normally we use red for plus and black for minus. So this, if you look at the top, when you pop the door open, you'll see a L plus and an M, and it's got an arrow pointing in. So this is where we're going to have to apply the 24 volts. So we'll do it with these guys right here, these power supplies. These, what we're going to mount them on is these Festo boxes right here, and these have the power supplies built into them. So that's why it's got two power cords, one for the PLC and one for the power up the monitor. That makes sense so far? These are the 24 volts out. So when we set up our commons, we'll use these M's right here if we're using the internal regulator inside this, or we can use the power coming off here. So the only thing we're going to use on this one is the 24 volts coming in, and then we're not going to use the 24 volts coming out. We'll pick that up off the power supply for this. Now when we use these power supplies, we'll use that. That makes sense? And it's real neat, the little switch module just comes in and plugs in, and then it's got 8 switches on it, and then we can play around with it a little bit. So the first programs that we write, for the thing is going to be using the little switch. And we'll show y'all how to manipulate it, where instead of using, what I like about the portal is that instead of trying to put this tab bar across the top, what Siemens has done is put a bar, where is it at? Is they put a menu bar over here. So right there where it says, when we get our program, it'll have the instructions over there, so you can pop a tab open, and it's got the long list. It's really, I really like that. On the Siemens, you got to figure out that thing, or I think I showed y'all how to bring up the big box. It's got all the instructions on it, but it's all. But then you got to know the mnemonics, right? You got to know the mnemonics. So we'll show y'all what we'll do is we'll come in. We've got a little feel of this. We know a little bit about some of the terminology. We'll talk about the different things across the top. We'll hook up our first PLC. We won't hook up the additional IO module yet. We'll just hook up. We'll take the switches up, and we'll let you write a very simple program before we start that. Yeah, okay. Y'all learn anything today? You better do like that. Okay, guys. See y'all Tuesday. Y'all know Monday's no classes, right?